So here is Unit 2, Forces and Newton's Laws, Lesson B, Newton's third law, and free body diagrams. Right here are our learning targets for this lesson. You should pause the video and read through those before continuing. Okay, so Newton's third law simply states that if two objects interact, the force exerted on object 1 by object 2 is equal in magnitude but opposite in direction to the force exerted on object 2 by object 1. For example, if you're driving down the road and your car hits a concrete barrier, okay? The car exerts a force on the concrete barrier. The concrete barrier also exerts a force back on the car. The main point behind Newton's third law is that forces always come in pairs. For every force, there is another force in the opposite direction of equal magnitude. If you push on a wall, the wall pushes back on you. So what we can do is we call every force then part of what's called an action-reaction pair. And one of the most important things to remember about action-reaction pair is that they always act on different objects. Okay, that's key to understanding Newton's third law, is that every force is part of an action-reaction pair, and these action-reaction pairs always act on different objects. So for example, take hammering a nail into a piece of wood. To accelerate the nail and drive it into the wood, the hammer exerts a force on the nail. According to Newton's third law then, because there is a force of the hammer on the nail, there must also be a force of the nail back on the hammer of equal size, opposite direction. So the question then becomes, how is it that the nail even goes into the wood in the first place? If the force that the nail exerts on the hammer is equal to the force the hammer exerts on the nail, why doesn't the nail just stay at rest? So in other words, when you hit a nail with a hammer, the nail pushes back on the hammer. Why doesn't the hammer just bounce away? Well, to answer this, we have to look at just the forces acting on just the hammer. Okay, just the nail. So when we start to look at the forces acting on just the nail, we'll be able to figure this out. So from the nail's perspective then, it is experiencing a force from the hammer on the nail, and the nail is also experiencing a force of the wood back on it, because as the hammer pushes down on the nail, the wood pushes back up on the nail, and as we can see from this nail, from the nail's perspective, the force of the hammer on the nail is much greater than the force of the wood on the nail. So if we look at just the nail, we can see that there is this net force in this downward direction. Therefore, we're going to get an acceleration in the downward direction. So there's another way to look at this too. Let's imagine that our nail has a mass of like 1 gram or 0.001 kilograms, and the hammer has a mass of 5 kilograms. Newton's third law says that when the hammer exerts a force on the nail pushes back on the hammer just as hard. That is, the force of the hammer on the nail is equal to the force of the nail on the hammer in the opposite direction. So let's imagine the hammer exerts, say, a 20 Newton force on the nail, and let's look at the acceleration then for each object. For the hammer on the nail, the force of the hammer on the nail is equal to the mass of the nail times the acceleration of the nail, because we look at just the nail. So this 20 Newton force has got a mass of 0.001 kilograms. We've got the acceleration. This will give us an acceleration on the nail of 20,000 meters per second squared. On the other side, we've got the force of the nail on the hammer. Well, with this much greater mass relative to the mass of the nail, the hammer experiences a much less acceleration in the opposite direction. So as we can see from this, the acceleration of the nail is 5,000 times greater than the acceleration of the hammer. This is because there's such a huge difference in mass between the two objects. So the same force exerted on a larger mass produces a correspondingly smaller acceleration. Okay, so in your reading packet there is more examples of this concept that you should take a look at. Okay, so now we want to talk about free body diagrams. We've talked a lot about what is and is not a force, what forces do to an object, and now we're kind of ready to assemble our knowledge about force and motion into a single diagram that we call a free body diagram. A free body diagram represents the object as a particle and shows all the forces acting on that object. This is a very important skill to learn and become good at to solve force problems. So let's look at this example of this fellow on his rock climbing trip. Okay, so he's hanging here. He's got a rope attached to the rock here. He's got his foot on the surface of the rock cliff face. So if we look at the rope, so we've got this tension force in the rope. We've got his weight force from Earth's gravitational field pulling him down. We have a frictional force from the cliff pushing up on his foot, and we have a normal force from the surface of the cliff pushing back on him. Okay, now these are all the forces acting on just him. You have to remember that each of these forces, the friction of the cliff, the push of the cliff, the pull of gravity, and the pull of the rope, all have an action-reaction pair acting on a different object in the opposite direction. But we're focused just on this person here. So in a free body diagram is what we'll do is we'll shrink this object down to a single point mass and put all of those forces in their respective directions on that single object. And these here are our basic steps for drawing a free body diagram. We draw a picture of the situation. We identify all the forces acting on that one object. Choose a coordinate system. Often our coordinate system will be a normal coordinate. Sometimes we'll tilt our coordinate system if we're on a surface that is sloped. Okay, we'll draw vectors representing each of those identified forces, and then draw and label the net force vector on this. So if we looked at this example here, right, these forces are all drawn kind of in relation to their size, okay, and they point in their respective direction. So let's look at a simple situation. Here we've got a person pushing on a box. In this situation, we've got, if we're going to look at just the box, okay, so as far as the box is concerned, it's experiencing some forces. It doesn't care whether it's a person or an elephant pushing it. It's being pushed, okay. So it's got the force of this push in to the right. It's got its weight force. It's got its normal force, and it's got frictional forces from the ground going in the opposite direction. The way this free body diagram is drawn, then we're showing a net force to the right. Therefore, we have an acceleration to the right. And what that's going to tell us is that acceleration is a positive acceleration because it's off to the right. If, say, the push were in the opposite direction, okay, so we have our weight here, we have our normal force here. If our push were in the opposite direction here and our friction were over here, so here's our push and here's our friction, in that case our net force would be in the opposite direction, would be the left, and our acceleration would also be to the left and would be a negative acceleration. Thing to really make sure you understand is that our acceleration will always point in the same direction as the net force. And in this example here, all of our forces are happening at within our x direction and y direction. So let's look at what happens when we have a force at an angle. Like in this picture at the right, we have a person pulling a sled. We're going to draw a free body diagram for the sled. The magnitudes of the forces acting on the sled are 60 newtons by the string, 130 newtons by the earth, and 90 newtons upward by the ground. Okay, so let's start with the weight force, okay? Or this is the force due to gravity, okay? We call it the weight force. That force, we're told, is 130 Newton, and it points straight down. It's always important to remember the weight force will point straight down regardless of the tilted direction of our axes. Then we've also got, we're told, a normal force pointing straight up, and that normal force is 90 newtons. Okay? And then we have the forces the force of the string pointing this direction at force of the string, and that is 60 newtons. Okay, so one thing to look at with this example, if this pull was not happening, if it were gone, think about what if we have just the person sitting on the sled not moving anywhere. Think about the forces acting on it in that case. If the weight force is 130 newtons, in that case, if there's no motion happening here, they're just sitting, there's no pull, this normal force would also be 130 newtons. Okay, we would have a force, we'd have the 130 newtons there, and we'd have 130 newton normal force. So why is it that this normal force decreases when we add the pull? So think about that. The reason is, when we add this pull in, we're pulling, this pull happens at an angle, right? So it's got components of its force. We've got a component in this direction, we've got the force of the string in the x direction, and we've got the force of the string in the y direction. Okay? The force of the string in the y direction serves to decrease this normal force, and if we were to add up the force in the y direction plus the normal force, it would equal 130 newtons. Therefore, what we're given in this case is we're ending up with a total net force in the x direction, in the negative x direction, because of the x component of the force from that string. So therefore we have a net force to the left, and therefore our acceleration is also to the left. So take a moment in your reading packet. There's study question number 2. Take a second to pause video and answer that question. Okay, so now we want to look at identifying forces on interacting objects. These are objects that, two objects that come together and are exerting forces on one another. So in order to understand the motion of a single object subject to external forces, we took that single object to be a system and everything else to be the environment. Now we're interested in the motion of 2 or more objects that interact with each other. So we're going to expand our system to include all these interacting objects. For example, for a truck pushing a car over here, we could take the car and truck together as a system while the road and earth would make up the environment. Okay? With the system chosen in this way, we can make a distinction between 2 classes of forces, external forces and internal forces. External forces are forces on objects in the system that originate from outside the system. For example, the weight forces of the car and truck are external forces because they are the force of the earth on the vehicles. Internal forces, on the other hand, are forces between objects in the system. The force that the truck exerts on the car is an internal force between the 2 objects in this system. So Newton's third law tells us that every force is a member of an action-reaction pair. For an external force, a force of the environment on the system, then, the other member of the pair is a force of the system on the environment. So for example, we have these weight forces, right? The weight of the truck. That weight comes from Earth's gravitational field pulling down on the truck. Newton's third law tells us there must be an equal and opposite force to this weight. It is not the normal force, okay? The weight is a field force exerted on objects by Earth's gravitational field. Therefore, an interacting pair, or the action-reaction pair to a weight force, is going to be that force, that object pulling back on the Earth. So what does that mean? That must mean that if a weight force is due to the Earth's gravitational field, that must mean then that an object, any mass, has its own gravitational field that pulls back on the Earth in an equal and opposite direction. Think about that for a minute. So these forces on the environment, for example, the force of the truck's gravitational field back on the Earth, have no effect on the motion of the objects in this system. So, for finding the motion of an object in this system, we don't need to identify action-reaction pairs involving external forces. We do have to identify action-reaction pairs for the objects inside the system, for the internal forces. In fact, finding both members of an action-reaction pair made up of internal forces is crucial because both of these forces act on objects within that system and therefore affect their motion. Only after identifying such pairs can we use Newton's third law, which relates their directions and magnitudes. Let's look at an example. A horse causes a wagon to accelerate by pulling it with a horizontal force. Newton's third law says that the wagon exerts an equal and opposite force on the horse. How can the wagon accelerate? We want to draw a free body diagram of each object to show how the horse accelerates. So when we do that, here is what we should look at. Okay? So this horse pulls the cart. The cart pulls back on the horse. The horse pushes on the ground. The ground pushes back on the horse. That's something to get about propulsion. When you, even walking, okay, you take a step and you push down, you push back on the ground. What's propelling you forward is not your push on the ground. It's the push of the ground back on you. Okay. So if you read in your reading packet the bits of information on walking and rockets and those action-reaction pairs, you understand what I'm talking about. So here we have the horse pulls the cart pulls the horse pushes the ground pushes the horse. So our free body diagrams for the cart would look like this. Here we've got the weight of the cart, we've got the normal force on the cart, and we've got the force of the horse on the cart, and we got the force, frictional forces on the cart in the opposite direction. For the horse, we've got its weight, its normal force, the force of the cart back on the horse, and the force of the ground pushing on the horse. Our internal forces action-reaction pair here is going to be the force of the horse on the cart and the force of the cart on the horse. But what we end up with is, because of this force from the ground, we end up with an acceleration to the right by the horse. This force here of the cart on the horse, the force of the horse on the cart gives the cart the acceleration over here. These are an action-reaction pair, okay? But because of this external force on the horse, this internal force provides the cart the acceleration. So we have to look, in a situation like this, we have to look at the two examples, or the two objects individually. So in your reading packet then, there's study question number 3. Pause the video for a moment and try to give that a shot. Okay, so that problem there, we've got the two objects, we've got the force, we've got the vase and the acrobat. Okay, so for the vase, we should see two forces acting on it. The weight of the vase, here because of Earth's gravitational field, and the force of the head on the vase here pointing directly up. No net force here, so in this case our net force is 0, and same is true for the acrobat. Net force is 0, but the forces acting on them, we've got the weight force on the person, we've got the normal force from the ground on the person, and we've got the force of the vase on the head of the person. So here we've got the action-reaction pairs then, or the internal action-reaction pairs are the force of the head on the vase and the vase on the head.